2 factoring. Whoa. So the first thing we want to talk about when we talk about factoring is like the difference between factoring and simplifying. So factoring is something that we use for a specific purpose. There aren't any times other than in this chapter where you will factor just for factoring's sake. Like in this chapter, we have to factor for factoring's sake because we have to learn how to do it. But just like when you like simplified this fraction, the way that we did that was by using prime factorization. So we were like 3 times 3 times 5 over 2 times 3 times 2 times 5, and that allowed us to cancel things. So we wouldn't write 45 as 3 times 3 times 5 for any other reason. Like that wouldn't be like the final answer of a problem whose answer was 45, right? You see what I'm saying? But in this case, in order to simplify the fraction, it was useful to write 45 as 3 times 3 times 5. So the process of factoring the number 45 we used for a specific purpose. So we used it to simplify a fraction. The same will be true when we factor polynomials. We have reasons to factor polynomials. But in general, our final answers when we're working with polynomials will be in simplified form. So when we talk about simplifying, what we mean is to perform the operations that are given. So if I gave you the problem 2 times 3, and you said that was equal to 6, going from here to here is simplifying. That is performing the operations, right? So the number 6 doesn't have any operations in it that can be done, which means it's fully simplified. Whereas on the left, there's multiplication that could be done, and so it is not fully simplified. Going in the opposite direction is factoring. So in many ways, when we factor, we're unsimplifying an expression. But again, there are reasons to do that, like simplifying fractions, right? It's useful to have it all broken down in terms of factors so that we can cancel common factors. So factoring has a really important purpose in math, but it's not the same as simplifying. So when you read instructions, it's important that you read like how they want the answer. So if they want you to simplify the answer or factor the answer. We've gotten to a point where I can't just like give you something and there's just one thing you can do with it that will get you the right answer. It all depends on what we're trying to, like what the instructions say. So I can give you a polynomial and you can do simplifying, you can multiply, you can solve an equation, you can factor. There's all these different things you can do with the same expression. So instructions become really important because it's not like every expression doesn't just have like one answer. It depends on what we're actually trying to do with it. So in chapter 5, we'll be factoring polynomials, but you don't want to forget everything we learned in chapter 4 about simplifying, because we'll be doing both depending on the situation that we're in and what we're trying to achieve in the problem. Does that make sense? Okay, so let's talk GCF. So greatest common factor. Which we abbreviate GCF. Can also be called the GCD, which stands for greatest common divisor, but in your textbook they use the word factor. So when we worked with LCMs, remember that the LCM was the smallest number that was a multiple of a group of numbers. So for instance, if I have, let's see, 6, 12, and 15. So to find the LCM, we did prime factorization. and then we built the LCM. So we needed 2 times 3, and then from that factorization of 12, we're missing another factor of 2. And then from the factorization of 15, we are missing a factor of 5. And so our LCM is 60. That is the smallest number that all 3 of those divides evenly into. The greatest common factor is sort of the opposite. It is the biggest number that divides evenly into all of them. So just looking at 6, 12, and 3, can you think of a number that divides evenly into all of them?
6, 12, and 3.
Sorry, 6, 12, and 15. The answer is 3.
3.
It's 3, right? So 6 is divisible by 3, 12 is divisible by 3, and 15 is divisible by 3. So our greatest common factor is 3. So notice that the greatest common factor is always going to be smaller than all of the numbers because it has to divide into all of the numbers, whereas the LCM is always bigger than all the numbers because all the numbers divide into it. So if we look at our prime factorization, notice that 3 is the only thing that all of those prime factorizations have in common. You guys see that? So we can find the GCF using prime factorization just like we did with the LCM. But when we build the LCM, we need all of the factors, right? We don't have to repeat the ones they share, but we need every factor that's in each factorization. When we find the GCF, we just need what they have in common. So let's do an example with bigger numbers. Let's find the GCF of, how about 72 and 108. So I could list all the factors of 72 and I could list all the factors of 108. Remember, that was actually like the first problem we ever did in this class where we had to list all the factors of a number. However, that gets really tedious just to find the GCF, and it's much more efficient just to use the prime factorization. Just like when we did LCMs, it was easier to use the prime factorization than to list all of the multiples of a number. So 72 is equal to 2 times 2 times 2 times 3 times 3. And I'm doing that in my head just to save time, but just keep doing your factor trees until you don't need your factor trees anymore. 108 is 2 times 2 times 3 times 3 times 3. Yes. So the GCF is going to be what they have in common. So notice they both have a factor of 2. They both have a second factor of 2. And they both have a factor of 3 and a second factor of 3 in common. So they both have 2 factors of 2 and 2 factors of 3. And that's all they have in common, right? The first one does not have a third factor of 3, and the second one does not have a third factor of 2. And so our GCF is going to be 2 times 2 times 3 times 3, which is 36. And if we sort of look at 72 and 108, you can kind of see like 36 is the biggest number that divides evenly into them, right? Because 36 times 2 is 72. And the only bigger factor of 72 is 72 itself. And 108 isn't divisible by 72. Because doubling 72 would get you all the way to like 144, which is too big. So let's look at this in terms of some monomials. Let's find the GCF of 18 x to the 6th, 24 x to the 9th, and 66 x squared. So again, we're going to do prime factorization. I am not going to write out all those factors of x because that sounds like not the way I want to spend the next 10 minutes of my life. So we're just going to write those just as x to the 6th. Because we know that x to the 6th is just a line of 6 factors of x, right? There's not anything super interesting as far as having different factors when we factor it. When we factor the coefficients, that gets interesting because we're not sure what the factors are until we actually break it down. Whereas powers of x, we know it's just a bunch of factors of x. So I have 2 times 3 times 3 times x to the 6th. And then 24x to the 9th. That's 2 times 2 times 2 times 3 times x to the 9th. And then 66x squared is 2 times 3 times 11 times x squared. So again, to find the GCF, I want to identify what factors they have in common. So I see that they all have a factor of 2, and they all have a factor of 3. As far as the coefficient, that's all they have, right, in common. So I do notice, oh no, not even 2 of them have the same factors, right? So 18 and 66 don't have any more factors of 2. Neither 18 nor 24 has a factor of 11, and 24 and 66 don't have any more factors of 3. And so all they have in common is that one factor of 2 and that one factor of 3. So my GCF is going to have a coefficient of 6. And then how many factors of x do they have in common? 2, right? Whatever the lowest exponent is, that's how many they have in common, because if you have 9 factors of x, you definitely have 2. If you have 6 factors of x, you definitely have 2. But x squared doesn't have any more than 2 factors of x, so they have x squared in common. So as you're about to see, like often the GCF will be small enough that you can kind of figure it out just by looking at all of them. In fact, in this one, maybe you could have just seen that it was 6 just by looking at it. But knowing how to do it from prime factorization is helpful if you encounter polynomials that have larger coefficients. So it's always something you can fall back on. Questions on this before we see how we use it?
Yeah, I thought before it was you're circling the pairs.
Yeah.
Like the last one was 2 times 2 times 3 times 3. So why is this only 2 times 3? Because like why wouldn't it be like 2 times 2 like that?
So these ones have 1, 2 factors of 2 in common, and 1, 2 factors of 3 in common. It's not, I didn't use 2 2s because I didn't take 1 2 from each.
Gotcha.
I just said they, right? And so here, all of them have 1 factor of 2 in common and 1 factor of 3 in common. Great question, thank you. Any other questions on finding the GCF? Okay, so then let's talk about how to use factoring out the GCF. So the first step to factoring any polynomial, after we've gotten it in the form that we want it to be in, which we'll talk a little bit more about in a second, is to factor out the GCF. This serves a few purposes. One is that it's not fully factored if you haven't factored out the GCF, and the other is that it makes the coefficients smaller so that they're easier to work with for further factoring. So to factor out the GCF, we just think about the distributive property. So if I were to simplify this, I would say 3 times 2x is 6x, and 3 times 5 is 15. So going from here to here is simplifying, just like we said before. When we undo the distributive property, that's factoring out a common factor. So going from here to here is factoring. So if I was given 6x plus 15 and I was asked to factor it, I would say, okay, the GCF of 6x and 15 is 3, because they don't have any factors of x in common, but they do both have a factor of 3. And so I can rewrite 6x plus 15 as 3 times whatever polynomial we would have to distribute to in order to get 6x and 15, right? So when I do this, I write, there you go. I say, okay, I see that my GCF is 3, so that's the greatest common factor of my 2 terms. And then I know I'm going to have 2 terms with addition between them, because my original polynomial has 2 terms with addition between them. And I ask myself, what would I have to multiply 3 by to get 6x? 2. Is that all? X, good. And then for the second term, what would I have to multiply 3 by to get 15? 5. And so we're just doing that distributive property in reverse. So we're undistributing. If you always want to check to make sure that what you have in the parentheses, that those terms don't have any common factors. That's how you know that you took out the greatest common factor and not just like a common factor. Like if we'd pulled out, well, in this case, that's all we can pull out is a 3. But if we ended up with like 4x plus 10 in the parentheses, I'd be like, oh wait, those both have a common factor of 2. And so we didn't pull enough out. So let's look at these same terms, and we'll say factor (24x to the 9th plus 18x to the 6th minus 66x squared. So I'm using the same monomials that we used to find the GCF before, which means we already know what the GCF is. Our GCF is 6x squared. So we've got 6x squared. And then in parentheses, what would I have to multiply 6x squared by to get 24x to the 9th?
4x to
7? Everybody see it? And then between the first and second term, there's addition. And then what would I have to multiply 6x squared by to get 18x to the 6th?
3x to the 4th.
Mm-hmm. And then between my 2 terms, or the second and third term, is subtraction. And then what should that last term be?
11.
Yeah, just 11, right? Because we pulled out both factors of x, and so there's no factor of x, so it's just the 11. And if we look at these 3 terms, notice that they don't have any factors in common. 4, 3, and 11 don't have any factors in common. And then one of them does not have a variable factor, which means there's not a variable factor I can pull out of all of them. And that tells me that I took out, I mean, I know I took out the greatest common factor because I found it already. But if there's any doubt, you want to make sure that you double check that you took out everything that you can take out. Does this we'll do more, but does the general process make sense? One thing you want to notice is that the polynomial in parentheses always has the same number of terms as the polynomial we started with. So if we started with a polynomial that has 2 terms, you have to have 2 terms in the parentheses. If we start with one that has 3 terms, you have to have 3 terms in the parentheses. The place where that gets a little tricky is if you have something like eight x plus 4. So what is the greatest common factor of 8x and 4? 4. So if I want to pull out a 4, what's my first term going to be?
4x. Or 2x.
2x, yep. And then if you take a factor of 4 out of 4, what are you left with?
1.
Yeah, 1. So we need that 1 there because it's like a placeholder. There has to be something to distribute to get this term. Because if we just said this, if you simplify that, you don't get 8x plus 4, right? So that second term doesn't ever go away. Even if you pull out the entire thing, you still are left with a factor of 1. So here's one for you guys to try. Let's see. Factor 2x to the third plus 10x squared plus 16x. So try that one. Remember, identify what your GCF is first. That comes out in front of the parentheses. And then like your leftovers go in the parentheses, whatever polynomial it is that you get when you pull that factor out of each term. Good. So we had 2x and then times x squared plus 5x plus 8. And I think that's what I saw in everybody's when I walked around. So there's a couple things to keep in mind about factoring. The first is, well, here, let's start a new page. So our general factoring strategy, we're going to build over the next couple days. And I'll have a handout for you on Thursday that wraps it all up. So you'll have it all in one place because we'll kind of add to it over the next couple days. So the first thing you want to do is put the polynomial in descending order. So for example, if you were given to the third minus 3x squared minus 12x to the fourth plus 15x to the fifth, to factor, the first thing we would do is rearrange this. So remember that the signs stay with the term. So if there's a negative in front of a term, it has to keep a negative in front of it regardless of where in the polynomial I put it. So the largest degree is that 15x to the fifth. So we'd write 15x to the fifth minus 12x to the fourth plus 27x to the third minus 3x squared. The big thing, again, to keep in mind as you do this is that the signs have to go with the term. So you don't want to mix up your signs as you're rearranging. So that 15x to the fifth stayed positive, the 12x to the fourth stayed negative, the 27x to the third stayed positive, and then the 3x squared stayed negative, even when I moved it. So then the next thing to do is to factor out the GCF. So in this case, what's my GCF?
3x squared.
Yep. So 3x squared. And I get 5x to the third minus 4x squared plus 9x minus 1. Yeah?
Yes.
So one other hiccup that we need to think of is we have 45 minutes to go. If that's all there was, it'd be pretty boring. So the other thing we have to think about is signs. So in order for all of our factoring strategies to work out nicely, we always want the first term to be positive. So the only time you ever factor out a negative number is if the first term is negative, because factoring out a negative will make it positive. So for example, if I want to factor negative 3y to the sixth plus 5y to the third minus 2y, notice that the first term is negative, and so I will factor out my GCF is y, right? That's the only thing they have in common is a single factor of y, but I'm going to take out a negative y rather than a positive y because it's going to make the first term positive when I do that. So if I take out a negative y, that changes the signs of all of my terms. So this becomes a positive 3y to the fifth. This becomes a negative 5y squared, and then this becomes a positive 2. And the purpose of taking out that negative along with my y is that it made this first term positive. And that's our goal. So the polynomial in parentheses, the polynomial we're factoring, we always want the first term to be positive. So to have a positive coefficient. So when we factor out the GCF, we want to factor out a negative if necessary to make the coefficient of the first term positive. And sometimes that means just factoring out a factor of -1. So for example, if we had negative x squared plus 6x plus 9, well, x squared, 6x, and 9 don't have any common factors, right? So there's no GCF that I can pull out other than 1. So 1 is a factor of everything. But I want that first term to be positive, and so I have to factor something out in order to change all the signs. So in this case, we would just take out a factor of -1, which will make this guy positive, this guy negative, and this guy negative. So even though the actual terms didn't change, the signs of each of them did. And again, the purpose of that is to get this first term to have a positive coefficient. And as we keep going, you'll see why that's more convenient. It's just all the strategies that we're going to use to factor these guys further get pretty messy if we have too many negatives floating around. And so having that first term be positive is going to make things a lot less complex for us as we keep going. Questions?
So you just pull the one out of the thin air then, right?
Well, I mean, it's not out of thin air. Like
Well,
one is a factor of everything, right?
Well, you used y on the other one and you subtracted that out of the,
Well, so here, because here they had a common factor of y. Here, all three of them have a factor of y. Whereas here, all three terms don't have a factor of x, so I can't pull an x out. So what I really did here was I pulled out a negative 1y, right? So I pulled out a coefficient of negative 1 and then a variable factor of y. So the coefficient is going to be the GCF of that negative 3, 5, and negative 2, which in this case is just negative 1. And then they all contain a factor of y. Whereas here, negative 1, 6, and 9 don't have any common factors other than 1. So we pulled out a negative 1. And then they don't all have a variable factor, right? If one of your terms doesn't have a variable factor, you can't pull out a variable.
what was the last example?
This one?
Okay.
Okay.
So that's why the y is missing off the 2.
Right, we factored a y out of each term. Good. So try this one. So factor So look at your general factoring strategy and make sure that you're following. Let's factor x to the 4th minus 2x to the 3rd minus 2x plus 10. No, plus 4. Is it in descending order?
Yes.
Is the leading coefficient positive?
Yes.
Is there a GCF I can factor out? There isn't, right? So I mean from the whole thing. So if I look at all of the terms, they don't have any common factors. So now how many terms do I have? 4, so we're going to factor by grouping. So we look at the first group and the second group. When I factor x to the 3rd out of the first group, we get x minus 2. And then remember, the operation between the groups stays. So this is a negative. And then the GCF is 2. But notice, like, if you remember how we did this when we distributed, if we were distributing that 2, we would really distribute a negative 2, right? Because of that minus. And so when we pull out that 2, we're actually pulling out a negative 2. So that makes this x and this negative 2. Always double check your signs, right? If I put a plus right here, distributing would not give me that positive 4. It would give me a negative 4. So that's why we have to change that sign so that it's actually equal to what's above it. So now I have a common binomial factor of x plus or x minus 2. When I pull it out of the first term, I get x to the third. There's subtraction between my terms, and when I pull it out of the second term, I get 2. So like most things we've done, the tricky parts to this come up often with the signs, right? You just have to be really careful. And what I do is, like, I always double check. Like when I'm in this step right here, I always double check that if I distribute that x to the third back through, I actually get x to the fourth minus 2x to the third. And if I distribute that negative 2 back through, I actually get that negative 2x plus 4. Just to make sure my signs are correct. So just kind of in your head, just think of doing it in reverse. So just distributing again, and make sure you get what you started with before you keep going. The most common mistake is trying to force it to work, like when it doesn't actually work. For instance, I could give you one really similar to this, like x to the third minus 2x minus 4. And if we try to factor that, we factor out x to the third and get x minus 2, and then we factor out a negative 2 and we get x plus 2, right? And so we double check that all our signs work. Don't try to force it to work if it doesn't. Like if there's not a minus 2 there, there's just not a minus 2, right? Like we can't somehow make it work by moving signs around. Either it does or it doesn't. So this just doesn't factor. And that's okay. Like some polynomials don't factor, just like some numbers don't factor, right? That's what allows us to factor things completely, is the fact that we can actually get it down to factors that cannot be factored anymore, which we call prime. And that's true with polynomials too. A polynomial that can't be factored is called prime. Okay, try this one. Let's factor Okay, so you guys are going to tell me how to do this. What should I do first? Put it in descending order. Very good. So 4x to the fourth minus 16x to the third minus 18x squared plus 72x. Okay, look at your factoring strategy. What should I do next?
Factor out GCF.
Yes, I need to factor out the GCF because notice that all of these coefficients are even numbers, so they have a common factor of 2, and then they all contain a factor of x. So I'm going to factor a 2x out. That gives me 2x to the third minus 8x squared minus 9x plus 36. So now we're going to look at this polynomial and continue with our next step, which is to ask how many terms does it have. So when you do like prime factorization, like if you're asked to factor the number 20, you would be like, oh, 20 is 2 times 10, right? But is that done? It's not done because 10 can be factored more. So we did the same thing here. We said, okay, I can factor out a 2x, but potentially that polynomial in parentheses can be factored more. So it has 4 terms. So I'm going to factor by grouping. This 2x just hangs on for the ride. And I use big brackets here so that I can distinguish them from all the parentheses that I'm going to write. It can get kind of confusing when you have a ton of like 3 sets of parentheses floating around. And so when I look at this polynomial, I have my first group and my second group. So I can take 2x squared out of the first group, and I get x minus 4. And then there's subtraction between my groups, common factor of 9, so I'm really taking out a negative 9, and I get x minus 4. 2x is coming along for the ride. And then common factor of x minus 4. And we have 2x squared minus 9 left over. And in this last step, notice that I don't actually need those brackets anymore. So in the previous step, I had this subtraction here, so I needed grouping. But here, this is all multiplication. So when you get to this final step, you don't actually need brackets to separate that 2x from what you get, because that's just all multiplication. Make sure you bring your GCF with you through each step. I can't tell you how many times on a test somebody correctly factors out the GCF at the beginning and then like completely loses it like through the rest of the problem, and so it's not in their final answer, which is always makes me kind of sad because I can see that they were doing it right, but they didn't end up with all the factors they needed at the end. Questions? So this is just combining both things that we've learned. So how to factor out the GCF from the whole thing, and then how to factor a 4-term polynomial by grouping. We're just doing it in steps. So if this 2x wasn't here, then this problem is exactly the same as the ones we've done for the past few examples. Questions on that? Or where everything came from, where everything goes? Okay, let's do one more, and then we'll be good for the day. So let's factor do negative x squared minus, oh, this is a good one to do. What should I do first?
So it's in descending order,
Yes.
and so we need to get our GCF,
Mm-hmm.
but we see that it has 4 terms.
It has 4 terms. Is there a GCF I should factor out before I factor by grouping?
If you can.
Negative.
Yeah, we need to take a negative 1 out, right? Because we want that first term to be positive. So we're just factoring out a negative 1. So x squared, that changes all of my signs. There's no other GCF to factor out. And now we can carry on with our 4 terms. So we can look at this guy and this guy. So that first term, or the first group, has a common factor of x. Then there is addition between my two groups. Always keep that sign. And then x minus 2, so I don't have any common factors that I can take out of that. But I do, thinking ahead, I want something there, right, when I factor out the x minus 2. And so this is the only time when we, like, write a 1. Just because it gives me something left over when I factor out that x minus 2. So now we have negative 1, our common factor of x minus 2, and then x plus 1. So like you don't have to write that 1, but it just gives us something like visually so that we know that that second factor is x plus 1. We don't lose any factors. Just like earlier when we, like right here, we had to have that 1, or else it wouldn't be equivalent. So the same thing is true here. So just visually, it's kind of nice to write it so you can see what's left over. Questions? Feel good about it? Hello?
Could you explain the one better?
Sure. So when we factor here, let's just, to simplify matters, let's just get rid of this negative 1. So I could have just said this is x times x minus 2 plus x minus 2, right? That would be true. However, when we go on to the second step, it's a little bit difficult to see that I have that common factor of x minus 2 because it's like not in parentheses. I could instead just write it in parentheses, right? And then when I pull it out, well, what's left here when I take out an x minus 2? There's an x. And then between my two groups, I have addition. And then what's left here when I take out an x minus 2?
Nothing.
Nothing, right? But really, it's a factor of 1. Like, dividing by x minus 2 doesn't give me 0. It gives me 1. Right? So I need something to distribute this to in order to get this term. So I have to think, like, what would I multiply x minus 2 by to get x minus 2? What would I multiply x minus 2 by to get x minus 2?
What?
1. And so that gives me a 1 right there. And so just to see that more, like, just more obviously, when we can't factor anything else out, we often just write that 1 just so we can visually see it. You don't have to write it, but you don't want to forget it either when you get to the next step. Does that make more sense? Because remember when we first started, I said, like, what's in that second set of parentheses is exactly what you get if you take that factor out of both terms. So if I didn't have that factor of 1 there, then I would just have nothing in that second term when I take out my common factor. Yeah?
So is that used for every case that would end up like that?
Well, all we're doing is we're saying that the biggest common factor that x and 2 have is 1. If there's another common factor, I would pull that out. Like everything has a common factor of 1.
Right.
So since I can't take any other, there's no bigger common factor for x and 2. So the greatest common factor that x and 2 have is the number 1.
Okay.
So instead of pulling out a 9 like I did up there, because that's the greatest common factor, I pulled out a 1 because that's the greatest common factor.
All right.
It's just that we don't normally pull out ones. This is the only situation where we do it, and it's just like a visual thing. Like, I could have pulled a factor of 1 out of this and written it like this. But in that setting, it's like kind of pointless.
Yeah.
Because it doesn't do anything for me. So we don't typically pull out factors of 1, but in this situation, it gives us a visual reminder of what that term is going to be in our second factor.